Okay. Today, although we said that we will talk about neural network, we will come back to neural network later because we have something which we must cover and it plays a very important role. And it is actually the second part of today's lecture. We start by talking about hidden micromodel and then the ensemble-based systems in decision making. Now, we understand when we come to the questions of recognitions and classification, we are dealing with lots of guessing. And because we are dealing with lots of guessing, it means probability is playing a very important role. We try to make this probability goes to 1 as much as it is possible. We have seen several techniques. You have done some homeworks. We are seeing another methods. We will talk about some other methods also in order to make some decision. The question is that which decision-making algorithm is the best? We have seen that, let's say, support vector machine as a classifier was very good. We have seen that you can use PCA for classification. At some point, it really performed very well. We have seen that there are lots of probabilistic models that we can use. We will see that the hidden macro model can be used in order to make a probabilistic model of our system and guess what is the class that we have to go. We have seen some clustering technique. But the question is, if I give you some data, which technique do you need to use? Imagine you have been approached by a biologist who says that, oh, you know, I have lots of type of batteries and I need to cluster them, or I know some samples I need to recognize or classify the next bacteria that comes, which class it has to go. Then the question is that which of these methods should really be our first approach? We understand some of the techniques like SVM with high probability will give us very good results. But is it enough, or can I have some other alternative? This is where this ensemble-based systems comes in. What we want to do is this. What will happen that I actually give a good credit to all the classifiers that I have, no matter if it's a good classifier or if it's a bad classifier. I mean, okay, if it is a strong classifier or it is a weak classifier, because good and bad are very political terms. So what will happen if I say that, hey, everybody, welcome. And then I look at all the decisions, and by looking at all these decisions, I will make one decision. We know that, you know, democracy, that we try to put into many countries. What was in democracy? We don't have it in this classroom because I'm fixing the data, I don't ask your opinion. But in general, we are asking, okay, what do you want? Should we continue the class? If the majority says yes, some people will say no, and we say that because the majority says yes, we continue the class. Right? So this is one way. And do you know what I do in here in democracy? We say that every person as a classifier is welcome. And then I look at what is the majority of this classifier is saying. So this is a very trivial way of combining all the decisions. It's called majority voting. Today we will talk about that one. Another form is that I can say that, okay, should we continue the class, but I have a few students which I like them the most. So although majority will say yes, but because those favored one says no, I will say no, we don't have a class. So it means that I give some weight to some of them more, right? And it's called weighted voting. So it means that some people have higher priority. This can be very logical because we know that, let's say, support vector machine is very good, and PCA is very kind of big. So what we do when we want to combine the decisions, we say that, okay, support vector machine, you are my favorite one. Whatever you say, I consider as twice that person. So there are lots of ways of combining these things. So we will see what are the methods that we can combine. Although we will talk about a few, they will be the basic ones. There exist lots of other techniques in order to do this combination. It's called boosting the decision. Remember, the whole idea comes from here. Do you know an ant is very small and it's very big by its own. But the army of ants has become very strong. So it means that the army of the big classifier will become a very strong classifier. That's what we have in random forest, right? We have lots of big classifiers, but when they come together, they will become very strong. The reason behind it is also this. Maybe, they said that when you want to make a team, make sure that your teammates, not two of the teammates, have the same ability. Imagine that he's very good in electronics and he's also good in electronics. Having them in one team will not really be beneficial. Why? Because already I have someone good who is in electronics. So maybe it will be good if I have someone good in electronics, someone good in programming, and let's say someone good in mechanics, so they can kind of complement their weaknesses. So the same thing is valid. Maybe I have a classifier who can do the classification very well. If the people have, let's say, all bright color schemes in the face recognition. I have another classifier who is in general big, but it can handle, let's say, the darker skinned people very well. So it means that if I have somehow combining them, I can handle the bright person already, I was handling them. I can even handle the people with the darker skin. You will see a few examples towards the end of the lecture. So you see there are lots of motives that we have behind it. Now in order to come to this one, let's talk about another method which we can use in order to do the classification, which is known as Markov model. In probabilistic theory, they usually call it as a Markov chain. We will see how we can use it, and then we will continue by talking about this fusion of the data. Now, the idea of this Markov model comes from an issue that they had in probability. Usually, our estimation for next event depends on our current situation. Do you remember in decision tree when we were playing a game, we said that the next node, the next question comes based on the answer of the previous one. If we say that the question is that is the person alive or dead, and if the answer was dead, it will not ask, for example, is he, I don't know, doing something right now because the person is dead, right? Or if the person is alive, we don't ask that, did he die before age 90 or after age 90? Because the person is alive, so the question is not relevant. So you see that sometimes we are in a situation that we need to guess, but our guess depends on our situation, our current states that we have. In programming, we usually refer to this one into the what's called state machines. Like you have one state and you need to go to another state. Now what we do an example, a few examples, then we solve a few examples on the board in order to get this concept very well. But the hidden Markov model, the Markov chain is actually a very deep topic inside the probability. In a course that we have in the probabilistic modeling, we talk about this one almost like a quarter of the semester. So you understand that what we do here is very quick, abstract, because there are lots of mathematics and probabilistic theory behind it. Now, assume we have a forced situation for the weather. You know, in Estonia it used to be very snowy in December. It's very sunny and hot, but it used to be very snowy. Now, assume that they had these four type of weather, so we can establish something like this state machine, which we have sunny weather, cloudy weather, snowy weather, and rainy weather. So what we are doing, we are making something like this. If the weather is sunny, next time the weather can be also sunny, right? And it says that if the weather is sunny, the next day will be sunny, and as we look at here, there is no way to get out. Okay? So it's kind of, we call it, this is an absorbing state. Why it's absorbing state? Because if the weather is sunny, there is no way to go out. We understand this is a poet example. If the weather is cloudy, then we say that the probability, we have some probability that next day is also cloudy. We have some probability that the next day is snowing. We have some probability that the next day is sunny. If we can go out of a node to another state, it's a normal node. If we cannot go out, it's called an absorbing node. Again, this is something that we don't need to know. Then, if it is snowing, we have the same situation. The next day can be snowing, it can be cloudy, or it can be rainy. But in our example, it will never be sunny, and so on. Question that we are encountering with is this. If I tell you that today is cloudy, can you tell me that what will be tomorrow? So we have to find out a way in which if I look at all these states, I will be able to manage to guess what is the next day. Now, we have one very important assumption. We will do some numerical example regarding to this weather is this. We have this very important assumption that the transition probability, the probability that if today is sunny, tomorrow will be rainy, and so on, are independent of the time. In other words, when we are talking, I tell you that if today is sunny, 80% probability we have that tomorrow is also sunny. And if you ask this question next year, I will say the same numbers. It means that we assume these probability values are not changing over the time. In the reality, they do. But we assume they are not, so it will help us in order to estimate many things very well. Now, let's do a numerical example. And let me use the board. I forgot to bring the other. Marker. But let's do it in this board. Now, we have 4 states, right? And time t means current time today. Time t plus 1 means the next time, which is tomorrow. Okay? So let's have our states. We have sunny. We have cloudy. We have snowing. And we have rain. Okay? So let's see what we want to do. We want to make a full kind of state machine which tells us that when we look at it, we can guess, we can estimate what should be the probability of the next state. Now, a table like this is called a transition table. Why we call it transition table? Because it tells us how we are time t. We translate to time t plus 1. It says that if today is sunny, tomorrow to have a sunny weather, the probability is 0.6. Now, from one state, when I go to itself, we usually show you with this type of arrows, right? And what is the probability value? 0.6. Then it says, if today is sunny, if we go to tomorrow, in order to have it cloudy, it will be 0.3. From sunny to go to rainy, the probability is 0.1. And if today is sunny, there is no way that tomorrow will be snowing. Okay? So this is with sunny. If we have an absorbing node, can you tell me that how the first row will look like? It will be, when we are going back to our own state, it will be 1, the rest will be 0. Remember, in the transition matrix or transition table, the summation of any row will be 1. So the summation of these values is 1, the summation of these values is 1, the summation of these values is 1, and so on. Right? Now, next one. If the weather is cloudy, the probability that the weather is sunny is 0.2. The probability that it will be also still cloudy is 0.4. The probability that it will become rainy is 0.3, and the probability that it is snowing, it is 0.1. Now, the next one is when we are rainy, the probability that it will be sunny is 0.1. The probability that it will be cloudy is 0.2. The probability that it is still rainy is 0.5. And the probability that it goes to the snow is 0.2. And finally, if it is snowing, the probability that next day will be sunny is 0.0, which means that it's not possible. If it is snowing, the probability that next day is cloudy is 0.3. Probability being rainy is 0.2. And probability being snowy is 0.5. There are a few things that you have to keep in your mind. If from sunny to snowy is 0, what can we say from snowy to sunny? No, we cannot say anything. From node A, maybe I cannot go to node B, but from node B, I can go to node A. What is important is that this summation should be 1. Okay? Is it true to say that the probability of coming back to the same state, like today I am here, I am this, and tomorrow I am the same thing, is always higher than the other probabilities? No, again, there is no such a rule. Can we have this main diagonal to be 0? Yes, this is also possible because they are all probability values, right? And these are only some example numbers that we have put in. So one important thing is that we have to be able to draw this state machine or to draw this Markov model. Why it is very important? Because if we know a transition table like this, or transition matrix, which we call it P, and if you give me one input value for each of, because each of these ones are already probability values. If I know the probability of today, the probability of today to be sunny, or today to be cloudy, if I know it, I can tell you that what is the probability of tomorrow to be sunny and so on. So by having this transition table, I can guess what is the next week or next day's probability. In other words, if I know what is the probability of recognition of each of these features, or classification of each of these features correctly, I can understand what will be the probability of the next ones and so on. This is playing a very important role. Actually, Peter-Markov model is used quite frequently for, do you know what is the most famous application of it? You know, we have this application that I talk and it writes. So when I say, for example, hello, it understands the word is hello. So in order to recognize the words, one of the most strongest techniques that we have is actually this Peter-Markov model. We have some slides about that one, and I will show it to you. Now, let's do some examples, some other example on the board. This is a kind of a quiz type of question. So I will write them on the board. I give you a few minutes and I want you to solve it. But I need to switch off this one. These questions will be very similar to what you might see also in the examination. So the quiz is this. Martin, given that probability of having head is pH, draw the Markov model for tossing a coin. Right? The most simplest probability question, I have a coin and I toss the coin. And we know that if it's a fair coin, probability of head is 1/2. But here, we don't know if it's fair coin or not. I said that the probability of head is pH, and I want you to draw this Markov model. Do you have anything to write? So you have an absorbing node. Do we have an absorbing node? In other words, if I have head here and I toss, I will get head.
Depends on whether you know in what state the coin is or not.
No, right now I put a coin, so I can see what it is.
It's different.
So, but what you have drawn shows me that we have some absorbing node. So it means that you have not drawn it correctly.
I know, but I assume that we first don't know the state of the coin.
We don't know. We put a coin, then before I toss it I can see it, of course. But
then it's in the super state. You don't know whether it's head or tail.
we never, when we have a model like this, we do not mention where is the starting point, right? So in other words, you have to draw it properly. So I can start from here, or I can start from here, or I can start from here, or I can start from here. Can you tell me that where I am starting?
From the unknown state.
Either heads or tails.
Yes, it's either head or tail.
Yeah, in that case.
We don't have we don't have probability for tails.
We don't know what is the probability of, number-wise, probability of head or tail. We don't know whether we start with a head or tail, but we know that we start with a head or tail, right? Like in here, we know that we will be one of these states, but we don't know which one is the starting point, right?
Can we use PT to denote probability of having tails?
Oh, wait.
Oh, okay, it's one.
Yeah.
1 minus P. Okay, yeah.
So how many states do we have? Two states. It's either head or tail, right? So as Javi and Eric had the conversation, if the probability of head is pH, can you tell me what is the probability of tail? So 1 minus pH, because we know that they are complementing each other. If it's not head, it's tail. Now, the question is this. If I start with the head, then I don't know whether I start with the head or tail. But let's say if I am putting the coin here and it is head, and I toss it. What is the probability to have head? So the probability of having head again is pH. What if I put head and I toss it and I get tail? So I will go to the next state with 1 minus pH. But I also understand that maybe I start with the tail. So if I'm starting with the tail and I toss it and I get tail back again, what is the probability? So this will be going back to this with the 1 minus pH. And if I have the tail and I cross it, and when I see the result, it is head, what is the probability? PH. Now, in order to check if you have done it correct or not, the probability of leaving from a state, the addition of them should be 1. This is leaving PH, this is leaving 1 minus PH. The addition is 1. PH plus 1 minus PH is 1. Same thing for the tail. Leaving is 1 minus PH, leaving is PH, the addition is again 1. So the Markov model is this. We do not know, Eric, that's true, we do not know from which one we are starting, but we know that we are starting either in here or in here. When you define an unknown state, it means it's another state. But it cannot be any of things apart from these two. In other words, we don't put the coin at its edge to toss it. Okay? I mean, you can, but we should not. Now, one other thing is, when we are talking about this Markov model, I talk about this transition probability transition matrix. The transition matrix is represented with P, and it has a form like this. In there, each row is indicating the current state, and each column that we have is representing the future state. And in this example, we have head and tails, right? And the future states are also heads and tails. Now, let's fill this P. Let's fill this P. Can you tell me that what are the numbers inside here? What are the numbers inside here? Basically, by looking at this model, you have to be able to fill P. If the current state is head, what is the probability of next state is head? PH. If the current state is head, the probability of having a tail is? If the current state is tail, the probability of having the next state to be H, it is? And this one is 1 minus PH. And we know that the summation of each row is equal to 1. Let's do one more example. Can I erase it? I have 3 doors. Each behind them there is a box and there is one person, Eric, Martin and Carter behind them. And I have the ability to mix them, right? I have the ability to mix them. So what happens is this, and the story is this one. We do a test, I put these people in there, we shuffle these boxes and doors, and we pick up one, okay? And we want to see what is the person inside there. Can you tell me now what is the probability of seeing Kadri? 1/3, right? Because they are all equal, so the probability of having them is 1/3. Now, the question changed. This was old high school. The question is changed. I open the door and I see this is Eric, right? I close the door, I already know this is Eric, and I shuffle it. And I bring and I said, okay, this one should be Eric, because I was following these changes. Although it was very fast, I tried my best. I bring it up and I open it. The question now is, what is the probability of having Eric? Right? Now, and I'm telling you the transition state is in this form. If I have some numbers, I have done some calculations, so I use the same numbers that I have. Let's put it in this order. When we open the door for the first time, and it is Eric in there, then probability of seeing Martin or Garvey in the next time that we open the door is 0.28 and 0.07 respectively.
Why?
What numbers do you like?
6% maybe.
Which one is 0.6?
One should be 0.66 and the other should be 0.3. Or 33, I think. Or
Tell me.
66.
66?
And 33.
33. If you want another number, we can put it. I wanted to use my number so calculation is easier.
But just why should we prefer one door to, or what's the reasoning behind the numbers?
These are no reason, just on this number.
Okay.
Just number. If in the first time we meet Cartwright, the probability of seeing Cartwright or Martin next time are 0.67 and 0.15 respectively. And if we meet Martin next time, the probability of seeing him or Cartwright next time is 0.52 and 0.36 respectively. Question. Draw the Mycroft model and find the transition matrix. easy. The question is very easy, but you have to read the story very carefully. There are lots of hidden information within this story which you need to, well, find them out. So, in order to solve a question like this, the best method is this. First, make the transition table. You know the table that we saw before? It has the sunny, cloudy, rainy stuff and with some numbers. Then, make the state machine. And then from the table already you can calculate what is the transition matrix. So we understand how many states do we have? We have 3 states. Eric, Martin, Kadri. So we have to make this table proper, transition table proper, so that we are not missing any information. Okay, you have, let's say, 3 minutes to do. Yes?
I didn't understand that we have 3 doors. We shouldn't consider those 3 doors, or what's up with those?
And he says that's part of the story. Just consider we have 3 states, and if we know what is the state currently, what should be the probability of having the next state? So the hint will be something like this. Field is table. Current state and future state. And the states are Eric, Martin, Kadri. Future states are Eric, Martin, Kadri. If there is any missing information which I forgot to write, you let me know. No cheating, Suman. Good. Okay, the 3 minutes is over. I can see from your facial expressions, some of you have done it, some of you are still surfing on the internet. But now, let's start, Eric.
Yep.
Let's start with Eric. It said that we open for the first time and the door it's Eric. And the probability of seeing Martin or Kadri are 0.66 and 0.33 respectively. So if I am Eric, the probability of seeing Martin is the first number, 0.66. The probability of seeing Kadri is 0.33. What about the probability of seeing it is Martin? Oh, sorry, it's Eric.
0.01.
0.01 because I understand this addition of all these, let's say PIs should be equal to 1. Right? So that's why those numbers. So what Eric wanted is this. If we see this is Eric, if you want to win the bet, don't say that this is Eric for the next time because the probability is very low. Now we continue and it says that we open the door and we meet Kadri for the first time. The probability of seeing Kadri again, the Kadri or Martin are this. So if I am Kadri, the probability of seeing her again is 0.67 and probability of seeing Martin is 0.15. So what is the probability of seeing Eric? 0.18. So if I am Kadri and the next time I meet Kadri and the next time I want to see it's Eric, the probability is 0.18. And it says that, but if we are, did I use the correct numbers? Yeah. Okay, and if for the first time we meet Martin, the probability of meeting him or Kadri are, okay, if I am Martin, the probability of seeing Martin again is 0.52. If we are with Martin, the probability of seeing Kadri is 0.36. So the probability of, if we are meeting Martin and the next time we are meeting Eric is 0.12.
Yeah.
Okay. The addition of all these rows should be 1. Good. So I can actually erase the whole story because I don't need them anymore. Now what I need to do is this. I have 3 states. Eric, Kadri, and Martin. And let's put the probabilities. If I am Eric, I'm sorry, if we are with Eric and we meet Eric again, the probability is 0.01. If we are with Eric, the probability of seeing Martin next is 0.66. If we are with Eric, the probability of seeing the next person to be Kadri is 0.33. We add these numbers, we see that the summation is 1. Let's go to Martin. If you are with Martin, the probability of seeing the next, if you open the door, is Eric is 0.12. The probability of seeing that this is still Martin is 0.52, and the probability that go back and see next person is Kadri is 0.36. And if you are opening the door and you see that that's Kadri, the probability of seeing that the next time again it is Kadri is 0.67. The probability to see next person is Eric, it's 0.18, and the next person is Martin, 0.15. So this is the Mycroft model. So what is the transition? What is the transition matrix? 0.01, 0.66, 0.33, 0.12, 0.52, 0.36, 0.18, 0.15, and 0.67. Now, we call it hidden Mycroft model, right? It's hidden because we actually don't have this, don't know which state we are at the beginning, right? We can estimate it. And let's do it in this form. Do you know, imagine you want to bet, like €1 each, you want to put it in the middle. If I open the door, which person will be behind the door? What is the probability that's Kadri, or that's Martin, or that's Eric?
0.
You're all in. But the thing is this. The initial probabilities are 1/3, 1/3, 1/3, right? We know that one. So the question is that if I open the door, what will be the probability of having, in other words, what is the probability in the next state to have either Kadri, Eric, or Martin? We understand by looking at this number, Eric has very low chance. So if you want to bet, if you want to put the money and you want to win, the hot chances are on Martin and Kadri. So putting money on Eric is a loss. It seems like. Why? Because the seventh state is very low. The probability from Martin or Kadri going to Eric is also low. We cannot say anything at the moment about Kadri and Martin. They have quite competitive numbers around themselves. So do you understand? Can you see that Eric is not a very hot choice? So probability from Eric going away is very high. In other words, from 1/3 going away is very, very high. So the question is how I can calculate it. Now, in order to do it, x1 is calculated by x0 multiplied by this transition table or matrix that we have. If this p, we said we assume it is independent from time. If it is independent from time, if I have initial one is 1/3, 1/3, 1/3. If I open and close the door 100 times, after 100 times, when I open the door, what is the probability of saying it is Eric or Kadri or Martin? In other words, what is the probability of xn? It will be x0 multiplied by p to power n. And this is true if p is independent from time. If it is not independent from time, in other words, if this table is changing every time, then it will be xn is x0 multiplied by p1, p2, p3, p4, and so on. Of course, we don't use that one. What we use is this. I want to see who is the have higher probability. So we need to do it. I'm sure that some of you have a calculator or some MATLAB open. Can you please multiply 1/3, 1/3, 1/3? This is a 3 by 1 multiplied by this. I mean, it should be transpose by 0.01, 0.66, 0.33. I'm sure that Martin, Eric is calculating it, right? You are the one who changed the numbers. This one transpose because the result should be 3 by 1 also. Or 1 by 3. So if we do, we get, come on. No one with MATLAB? This will be multiplied by this one, right? And we come in here. Then 1/3 will be multiplied by this one, and if we come here, then 1/3 will be multiplied by this one, and if we come in here. In other words, 0.13 plus this one, it will be 0.31 divided by 3, it will be 0.103. The next one is the addition of all these ones, and it is 67, it's 1,3, it's 0.6. 0.443, and the last one is 0.453. So as you can see, those who bet on Kadri, because we have Kadri the last, we win. As I said, it's very marginal to be between Martin or Kadri, but Eric is definitely out. I could calculate this one very fast because I understand the addition of all of these three should be 1. Now, any question? So in the exam, be ready about having a story which you need to do all these steps. Which you need to know to do all these steps. So let's look at a few application of these hidden micromodel. You also understand that all the numbers that I gave are just example. So hidden micromodel actually used quite a lot in many pattern recognition applications. And as I said, the most famous one is when we are doing this speech recognition. In the speech recognition, actually what happens is this: an speech comes, and already we have some words which are known for the system. And then we are trying to do two models. One is a language model, the other one is a logistic model. How it works is this. How it works is this. Each of the words that we have, its own model states. It has its own model states. In other words, when you want to say the word cat, for C, we have some models. For A, we have another model, and for T, we have another model. So we are checking if we are from this state. Do we go to this state? Do we go to this state? Or if you are making the model is the same as the model that we wanted to have, and we are matching based on that one. It's more complicated than what we are saying it right now, but the whole story is this. We are doing the comparison based on that. We are looking at the word cat, and we make the model, and we see that if it is matching with the model that we had previously, the logistic model that we had previously. Now, and as I stated very earlier, it's all working on the probability. That's why that if we are working with one accent, and if someone with another accent talks, it is tough to do the recognition, because the probabilistic model will be changing. For instance, if we are training for an Estonian language with the people who are living in the mainland, and then someone from Saaremaa comes and they cannot pronounce like me, that one, the tilde, so it will fail, right? And the same thing, if you are choosing it as, there are so lots of software, and you have to choose if it is British English or if it's an American English. Choose, let's say, British English and speak with an American accent, it fails miserably in so many words. So, other application of that one is on handwriting recognition, text generation. This software is actually freely available. You can download and use them. In gene technology, emotion recognition. So it's being used quite a lot. The reason that it's very popular is the whole nature of classification clustering is very high with probability. A hidden micromodel is a very strong probability tool that we have. As you have noticed. And many of the problems that we are facing with are time independent. In other words, you could use this xn is equal to x0 multiplied by p to power n. So if you have your very good p, you can estimate a variable. Now we are going to the next steps, next part of the class, and we are talking about this ensemble technique. We have talked about PCA, LDA, software vector machine, binary classifiers like this decision tree that we have seen, and so many other techniques, right? And the question was that how we can embed them, how we can make them come together in order to make a better decision. Or, when I was solving example, I was always giving you the two-class classifiers, right? What is the other name for the two-class classifiers? Binary classifiers. We were dealing with binary classifier. And I told you that it's very easy from binary classifier to go to another form of classifier. Because if we imagine we have the binary classifier, let's say binary SVM, And in order to make it multi-class SVM, we can always say that class 1 and not class 1. And when we are in not class 1, either we are in class 2 or not class 2. And we understand when we are in not class 2, we cannot be in class 1. If a member of class 1 is here, what does it mean? If a member of this class 1, which is supposed to be here, is here, what does it mean? It's a misclassification. So here it doesn't say that we don't have misclassification. We can have a misclassification. And misclassification comes at the point that when we're supposed to be in the green part, we have been kicked out and we are in the gray parts. So this is how we can, this is the easiest way to convert a binary classifier into a multi-classifier. There are lots of these algorithms, lots of logics behind it. If you remember at some point we said that how we are writing an algorithm is different from really the approach. Some people, because the nature of the data can change, sometimes the data, we can divide them or we can play with the data in a form that you understand. Sometimes it's bigger than some value or sometimes it's less than some value. So you can make going through this tree much faster in more appropriate form. So now that we have lots of classifiers, so we want to see how we can combine them. There exist several methods. We will talk about some, but these ones that we talk are very basic ones. I call them basic, but you can open a transaction paper and see that they are using it. They are very strong, but there exist more complicated techniques like auto boosting and so on in order to do this combination. We will talk about majority voting. We will talk about weighted majority voting. We will talk about mean rule, mean max median rule, weighted mean rule, and also product rule. We will see what are the advantages, what are the disadvantages. Now, why I combine this one with the hidden Markov model was this, to emphasize that the whole concept of recognition is probability, it's based on probability. With high probability, this person is erring, right? So although we are talking, we don't say that use the word probability when we were talking about the decision trees, but we are actually having probability inside it. Now, when we are talking about each of these methods, you will see that the formulation, we are talking about PIs, probability values, right? So it's very important for us to understand that when we say a decision, we are actually talking about a probability value. We are talking about a probability value. I already have, we will talk about the details, but I already have talked about this majority voting and weighted majority voting. Because it is a trivial solution if you have a multi-classifiers. You just listen to all of them and you pick up the majority of them. And, or you favor a few of them more and you listen to them more. Now, how come that I understand that I have to favor some of them more? You know, there are two ways of having multi-decision. One of them is, as I said, we have multi-classifiers. I use method 1, method 2, method 3. Like I use PCA, LDA, SVM for one question. Another form is I use one classifier, let's say SVM, but I solve this problem from different point of view. Imagine that I need to do the classification, face recognition, and what I do, I will do it, let's say, in R channel, in G channel, in B channel, RGB, you know, in color images, or in U channel, or in, I don't know, in S channels, or in I channels. So you see, I use one classifier, but I use it in different form. Or you use it from different, you use it in spatial domain, you use it in frequency domain, you use it in Laplacian domain, so you change your domain, the way that you are looking at this problem. So we use one classifier, but because we use it on different point of view, so we have different decisions. Or you can use different methods in different point of view, and then still you combine them. So you understand that there are several methods in order to make these multi-decisions. Now, the first one is majority voting. Majority voting is we have series of decisions. What we do, we are looking at which decisions has been repeated most. which decisions has been repeated most. So if you want to write a code, let's say you want to write a MATLAB code in order to implement majority voting, how do you do that?
Sum up the rows and compare.
Well, one way is that you can assign a counter for each of your classifiers or point of view of the classifier, and you will increment these counters if the decisions are the same. So at the end you see that how many class 1 we had, how many class 2 we had, how many class 3 we had, and so on. And the one which has the highest number of this counter is assigned, it is decided to be the most, the result of the majority voting. From probability and a statistic point of view, which operation gives us this? Mode. Mode in a statistic means the most frequently happen element. In other words, you can put all your decisions in a vector and find what is the mode of your decision. Okay? Now, in majority voting, we have to be careful a little bit. Imagine I have 3 methods, right? I have 3 methods, and I am using the program of face recognition. Method 1 says class 1. I have one test, it says class 1. Method 2 says class 5. Method 3 says class 20. So each of them, 3 methods, each of them says different. Which one do I have to pick? It's the moment that mode is become 1. In other words, I cannot make a decision. I'm asking that which day should the exam be, and each of you will tell me a single different day. So which one do I have to pick? Which decision will you pick out of these 3? It says class 1, this one says class 5, this one says class 20.
Your weight is not your value.
We are not talking about the weight at the moment, so you say randomly we pick one. This is absolutely one of the way, a naive way, but this is a way. What is a more clever way? You average them and find one. That was interesting. I never thought of that one. Okay, let's get back to this example that I asked, which day do we have to do the exam? And each of you give me a date, okay? First, second, third, fourth, and so on. And I have a day in my heart, which I want to do the exam. Imagine I am saying the tens. Let's do the exam on tens. And you say 1, 2, 3, 4, 5, 6, 7, 8. Let's say these people are saying. And I really wanted to do the tens. So which one do you think I will pick? Why?
Because it's the latest.
No, it's not the latest. It's the closest to my decision. Okay? It's closest to my decision. Now, keep this on your mind. So I have 3 classifiers and each of them tell me different things. Which one should I pick? We don't. Which one is closer to the real value? We don't know the real value, but we know something else. What is it? We said closest. Like 8 was closest to my day, which is 10. What is this value? 10 minus 8 is 2. What is the value for 2? We call it distance, but we have another name for that one. No, distance is correct, absolutely correct, but we have another value. We show it with the letter E. Error. It's error. So I have 3 values. I will look which one has the smallest distance to one of my training, or has the smallest error from my training. Imagine it says class 5, and the error or the distance is, let's say, 100. This says class, 10, and it is 1000. and this says class 20, and the error is 10, or the distance is 10. Although each of them are saying different thing, and I cannot say that this method is better than the other one, then I look at the error. This one seems to be closer. Not necessarily being closer is the best, but we have no other information. We don't have any other prior information, so we have to guess. You know, in the example of, is it Cartry, Martin, or Eric, we knew that Eric is very out, you know, so we should not bet. But Cartry and Martin were very close, so it really didn't matter. We have to bet on one of them and see actually what happens. So we will pick this one which is closer because it seems to be correct one, but maybe it's actually not. But we will pick if we have the mode to be 1, or assume we have 10 classifiers and 5 of them says class 1, another 5 says class 2, then we have to look at this minimum error. So question, 5 of them says class 1, 5 of them says class 2. Which class do I have to pick? I have 10 classifiers. 5 says class 1, 5 says class 2. Or I have 20 students, 10 of them says, let's do the exam on the 2nd. 10 of them says that, let's do the exam on the 8th. Which one do I have to pick? 1st or 8th? Which one will I pick?
Do you have a preference?
Yes, 10th was my preference. 8. Why? Because it has the smallest error. Now, this was a good example, but what will happen if I have 5 classifiers says class 1, another 5 classifiers says class 2? Can you define what is the minimum error? What we do is this. I add all the errors in the first one, so I get one value. Then I add all the errors in the second one, I get another value, and I compare this one. Which one is the smaller? The one which is the smaller, I will pick that one. There exists lots of other logic. Usually we go for the weighted majority voting, which we talk, but otherwise we have to look at these distances or errors in order to see which one we are picking up.
How do you handle equal distances?
If we calculate that this is also equal to that one, then you just pick randomly. But what happens is this. Although we said we have big classifier, I'm using SVM in let's say H, S, and I color channels, but I know I is better, for some reason, I is better to recognize. So the decision that I will give me is more valid than the decision of H and S and I. In other words, I can always say that whatever I says, it's like that I is saying it twice, right? So I can define a weight. So in reality, what happens when we have these weighted majority voting? How you can look at the weighted majority voting is like this. You can put the decision repetitively based on the weight. Imagine I have 3 classifiers, but this classifier has weight 3, or it's 3 times the weight is bigger than the other one. So what it means is this. I say that decision of classifier 1, decision of classifier 2, decision of classifier 3. So how many decisions do I have? 5 decisions. And then I apply majority voting. We understand that this example that I gave you, whatever this decision is, it will be picked up. But imagine if the weight of this one was twice of the other ones, so I would have 4 decisions, so I have to look at this one in order to make the majority voting. Or imagine you have tens of them, so some of them will be repeated twice, some of them will be repeated 3 times, and so on. So how do I know which classifier I have to pay more attention, or which channel I have to pay more attention? It gets back to your data, to your whole scenario that you have in your hand, right? So you cannot really, so the weights will be assigned by, let's say, experts. Maybe you are also finding a clever way of calculating the weight by using entropy and so on. I stop here. We continue on Friday by talking about different other ways of combining the decisions.